Hello friends, and welcome to in this week 7 of the course Wastewater Treatment and Recycling. We have started discussing about the various treatment aspects of wastewater, and we have discussed the preliminary treatment in the week 5, and then last week we took up the secondary treatment where we discussed the aerobic treatment systems. This week we are going to focus our discussions onto the anaerobic treatment of wastewater, and in this particular lecture we will start having an introduction towards the anaerobic treatment, what anaerobic treatment means and how it is employed or how it is used for the purpose of treatment of wastewater. So, to begin with, anaerobic treatment essentially means as we discussed that while discussing the different type of microorganisms, we did talk there are aerobic, anaerobic and facultative microorganisms. So, anaerobic microorganisms are those who works in the absence of oxygen. So, when they take part in any of the bio-oxidation reduction reactions, so it is not the oxygen, but other elements like sulfate, nitrates or those kind of things, they become the electron acceptor. So, anaerobic microorganisms primarily work in the absence of oxygen. Now, if we see the basic process of anaerobic digestion, so we have organic matter in the wastewater which we account as BOD or COD. So, when we are having this organic compound or organic matter in the wastewater, the anaerobic microorganisms degrade and decompose this in absence of oxygen, and the ultimate or the major bioproduct becomes the methane and carbon dioxide, which collectively is referred as biogas. So, essentially the anaerobic treatment is a sort of various collections of various steps or various processes by which these microorganisms or anaerobic microorganisms break down the biodegradable material present in the wastewater. Now, they break down in what? They break down in biogas. They break down in primarily biogas. Okay, of course, there is some cell formation, of course, there is some part will go in the effluent, but the major end product remains the biogas. So, the most of organic carbon is converted to biogas, while only little goes to the sludge production. So, that is what is the basic of anaerobic biodegradation. Now, before we go into the detail, let us have a look how they are different with the aerobic systems. Why we are saying anaerobic microorganisms are like end product is different. So, how it works in aerobic processes, we typically have the organic pollutant and oxygen converting to the water vapor, carbon dioxide and sludge. Okay. So, a significant mass about 45%, although this number varies though, but a significant portion goes to the sludge formation in aerobic systems. Okay. There is some organic matter or some BOD goes with the residual pollution. So, still like if you have say for say 100 milligram per liter BOD coming in, you probably will be able to remove 90 and 10 will go to the effluent. So, this is the residual pollution which is going along with the effluent, and then what is removed is basically distributed in the water vapor and carbon dioxide. So, on the name of gas, carbon dioxide is produced, which again has its own environmental footprints because it is a greenhouse gas. So, the carbon dioxide gas is produced and the significant almost half of that goes to the sludge. Further, there is requirement of air because the aeration needs. So, as we were discussing in the earlier week, for the purpose of aerobic system we need to supply air in some form or other, and that typically needs aeration, which again is an energy intensive process and expensive. So, we are actually supplying energy, and then as a result we are generating certain amount of biomass and certain amount of gas in the form of primarily carbon dioxide. Now, what happens in the anaerobic system is because it works in the absence of oxygen, so there is no air needed. So, the requirement of air is gone. So, the one which is a basically energy and cost intensive process in the aerobic system is not there in anaerobic system, that is one part, and then the amount of the organic matter which comes into the system, into the anaerobic system, part of that is converted to the sludge, anaerobic sludge, which is very less in quantity. So, you see here in aerobic system it was almost half of the one which is getting removed, 40 to 50% is converted into sludge. Here sludge conversion is just 5%. So, conversion to solid biomass is very little. The majority of the organic which is coming into the system is converted to biogas. Okay, and as we were discussing, biogas is basically CH4 plus CO2, out of which 60% is CH4 and which is a useful fuel. Okay, so which is a form of energy, in fact, if we can trap that. So, here we are supplying energy, and producing the carbon dioxide and biomass. Here we are not supplying energy, no energy supply is needed, but we are producing energy, and the biomass or solid waste produced is very low, there is higher degree of residual pollution though. Okay. So, this is what is the basic difference between aerobic and anaerobic system, and this difference, if you see, again these numbers varies from source to source, and if you see into the more detailed one, so like these are the couple of references from different sources. Okay. So, here you see that almost for a 100 kg of COD, the 60 kilowatt is the requirement of aeration. Okay. Then the significant amount goes to the heat loss, and around 30 to 60 kg of the COD is converted to biomass. Okay. So, that way in anaerobic system, if you again feed 100 kg of COD, same amount of COD, just around 5% of that means around 5 kg of COD goes here, around 15 kg goes with the effluent, and there is biogas generation, carbon dioxide, there is some carbon dioxide is generated also, but the significant amount of methane is also generated, which has a potential of around 280 kilowatt hour. So, giving 60 kilowatt, generating 280 kilowatt. Okay, here that is the basic difference. Okay, though these numbers vary. So, like here if you have a 100 kg COD inflow, the oxygen requirement was estimated to be the power requirement was estimated to be around 100 kilowatt hour, then heat loss and effluent 10 to 12 kg, the sludge 30 to 60 kg, whereas in case of anaerobic 70%, 60-70% is methane. So, the biogas form is 40 to 45 meter cube, and 10 to 20 goes to the effluent and 5 goes to the sludge. So, if we compare aerobic versus anaerobic treatment options, so the two things are crystal clear. Aerobic system needs significant amount of energy for the treatment itself in the form of aeration, and generate significant amount of solid waste in the form of sludge, if you consider that as a waste, and significant amount of carbon dioxide is generated, which is a form of greenhouse gas pollution. But if you compare that with anaerobic system, so here what you get, that the very little of sludge is generated, the majority portion, almost 80% of the total COD goes to the biogas, and of that 80%, 60 to 70% or even at times higher goes to the methane production. So, we are actually producing energy instead of consuming energy. So, obviously from energy perspective, the anaerobic systems are far more attractive as opposed to the aerobic system. okay, because aerobic system require energy, anaerobic system generate energy. Okay. So, that is the kind of difference. Okay. Now, if we see the advantages and disadvantages of anaerobic system specifically. So, anaerobic system, if you look at the advantages first, in the anaerobic system there is low production of solids, okay, almost 3 to 5 times lower than the aerobic processes. Aerobic process generate lot of sludge. Now, we need to basically handle the sludge, because then you have to have sludge handling facilities, drying beds or the dewatering mechanisms, then make that of sludge cake. If you are able to reuse it, it is fine, otherwise you go to find some landfill for where you can dump this sludge. So, there is lot of energy and environmental footprint of such sludge production as well, whereas which is very high in aerobic systems, but very low in anaerobic system, just 3 to 5 like very around 5% is converted to biomass and rest goes to the form of bioenergy or that way. Anaerobic system has low energy consumption, usually because as we were discussing, the requirement of energy is very low. Okay. We do not need to aerate anything. So, only the pumping cost is there, and apart from that there is no as such energy cost. So, the energy consumption is low, usually associated with the influent pumping station only, which leads to very low operational cost as well. So, your operation and maintenance cost is also going to be low. The land requirement is low, it is a simple tank kind of thing, and can be basically there are high rate anaerobic processes. So, they can in a compact fashion they can work at high rates, and the land requirement would be low. Construction cost would be low, we do not need mechanical equipments or aerator or diffuser kind of thing and then ensure oxygen supply. So, those things get away. Then the ultimate advantage is production of methane, which is having very high calorific fuel gas. So, that is one of the very distinct advantage which makes the anaerobic processes quite attractive. Then possibility of preservation of biomass with no reactor feeding for several months, okay, because the amount of biomass produced is very low. So, that much this thing can be retained inside the reactor, okay, and anaerobic systems are slow growers generally, that is why the growth is very slow. So, anaerobic species are slow growers, and at the same time their decay is also slow. So, even if like reactor feeding is stopped for few days, okay, for even for at times month, so they do not need oxygen to survive. So, that oxygen criteria is anyway not there, and even if some feed or the carbon source is stopped, carbon supply is stopped, still they can survive for several months. That gives a possibility of preservation of the biomass. So, biomass still remains active and still remains workable. There is a tolerance to high organic load, okay, it can actually sustain even high organic load. There is application to small and large scale. So, whatever scale we want we can apply it, and the nutrient consumption is relatively low. So, that is another advantage of this. Then if we look at the disadvantages part, we will discuss though some of these points in detail later on, but quickly to disadvantages part, the anaerobic microorganisms are susceptible to inhibition by a large number of compounds. So, some of the metals or toxic elements or those kind of things if present, they can inhibit the anaerobic microorganisms, and process failure or risk of process failure are quite high. Then processes startup can be slow in the absence of adopted sludge. See, because of the low growth or because of the low susceptibility of these microorganisms, what happens that if we start an anaerobic system where we have a seasoned sludge or the microorganisms that we put in are pre-acclimatized, are of the good granulation form. So, then this can be like this can take up quickly. So, startup period could be low for this one, but if we start with a sludge which is not adapted, which is not acclimatized to the system, then this acclimatization phase may go very long, and at times even 2 to 3 to 4 months, at times even 6 months it could take to basically your the reactor could take this much of time in getting stabilized at first hand. So, there is a possibility of high startup time if it is not being started up with acclimatized sludge, but this of course can be dealt with if we can bring in acclimatized sludge, or if we can start with the sludge which is already adapted to such conditions or to such waste. So, then the startup process could be quite rapid and we can actually achieve that within a few days span. At times, depending on the quality of effluent needed, many times some post treatment becomes necessary. Okay. So, as we were just discussing when the in the previous slide, the aerobic versus anaerobic treatment system, the effluent from aerobic treatment system have generally like of the order of 90% or higher removal, but in anaerobic system the removal efficiency is generally less than 85% or so, or definitely around less than 90% or so for most of the cases. Okay. In field, of course, in laboratories we can get a good removal efficiency with anaerobic system as well, but in field this kind of problem may arises. So, what happens when we are working with a waste which is having high COD or high BOD and we are not getting adequate degree of removal, so then the post treatment becomes necessary. The biochemistry and microbiology of this digestion process is complex and basically needs too much of control and those kind of thing, at times even like leakage or those kind of thing. Oxygen entry into the system can become toxic to the bacteria. So, they are susceptible to so many things, okay, so many metals, oxygen, those kind of thing, and there need to be further investigation to carry it out how we can reduce the risk of the failure of anaerobic system. There is possibility of generation of bad odor. So, the foul smell can also be generated at anaerobic sites, okay, although they are controllable, it is not that high. So, that is possible to basically deal with that. And then possible generation of effluent with unpleasant aspects. So, many times though, because it is coming from a system which is devoid of oxygen, so there might be some unpleasant aspects associated with such effluents in form of odor, in form of some of the insects coming in, or those kind of thing might be there, okay. And the removal of nitrogen, phosphorus or pathogens is not achieved from anaerobic system. So, that is another demerit of the anaerobic system. Okay. Why it is not achieved? Because of the nutrition, and because since the growth is slow, so the nutritional requirement is slow, so nutrient uptake is also slow. So, the enough nutrient is not uptaken by the anaerobic systems, and that leads to somewhat the not significant or not satisfactory removal of the these nutrients. Okay. So, now if we see the anaerobic treatment systems, so we discussed about some of the advantages, there are some disadvantages also, but still what is observed that anaerobic treatment systems are getting more popular. Okay. So, this is kind of number of installations, number of anaerobic plants across the year. So, we see that these numbers were more or less negligible till 1980 or so, okay. And then once we had a energy crisis and focus shifted more towards the renewable energy and reducing the energy. So, there has been a substantial rate of increase in the installation of anaerobic systems. Okay. So, there is huge number of anaerobic reactors came into the installation post say 1990s or so, and this number is still growing on. The major reason for this popularity is the less energy requirement, less operation and maintenance cost, and energy production, chances of energy production, making it the process self sustainable. Still it is not used or it is not applied to everywhere. Okay. The sewage sector has very limited anaerobic installations, whereas the industrial effluent treatment or the wastewater coming from the industry, the anaerobic process are far more attractive for industrial systems, and there has been quite a few number of installation in the different industry of the anaerobic processes of these anaerobic units. Now, if we see the process of anaerobic degradation of organic matter, what happens, how this gas is generated. Okay. So, then the typical degradation of anaerobic typical degradation by anaerobic bacteria would actually follow 4 different steps. So, there are 4 different steps, and that leads to the different type of microorganisms involved in that. So, these 4 different steps eventually is responsible for degradation or decomposition of the organic matter and converting them to the final end product. Okay. So, what are these 4 different steps or 4 different processes? So, the first step or first phase of anaerobic degradation is the hydrolysis. Okay. So, what typically happens, that the complex biopolymers or complex polymer or those kind of things. So, there is protein, polysaccharides, fats, oils, lipids. Okay. So, these things are first hydrolyzed. Okay. So, it was hydrolyzed, and there are fermentative group of bacteria involved in this hydrolysis process, which is essentially the transformation of your higher molecular mass compounds into the compounds suitable for use as an energy and carbon source. So, that is the major objective of hydrolysis. Okay. This happens, so that becomes the first step, first phase, and then what happens, that these hydrolyzed products, which then broke down to the monomers and oligomers. So, sugar, amino acid, peptides, these kind of things are formed. Okay. Then these are converted to the lower molecular mass intermediate compounds through the process of acidogenesis. So, that becomes the first phase, second phase or second step, the acidogenesis, where this sugar, long chain sugar, amino acid and those kind of things are converted to propionate, butyrate, those kind of fatty acids. Okay. So, that is the process of acidogenesis, and then the third step or third phase is acetogenesis. So, acetogenesis, where the lower chain volatile fatty acids produced like these these volatile fatty acids, these long chain volatile fatty acids are then further converted, long or intermediate chain volatile fatty acids are then basically converted to the acetate or those kind of thing. Okay. So, acetate or hydrogen are kind of produced from these volatile fatty acids. Okay. And that reaction is known as acetogenesis, or that step or that phase is known as acetogenesis. And then there is the last one, which is methanogenesis, the last phase of the typical anaerobic degradation process, where this acetate or hydrogen are converted into the final end products, which is methane and carbon dioxide. Okay. So, that way the complex biopolymers are converted to the final end product, methane and carbon dioxide, through a series of steps which involves hydrolysis as a first step or first phase, acidogenesis as a second step, then acetogenesis and methanogenesis. Okay. It is not this way, like these some of these sugar amino acid could directly be converted to acetate and this thing. So, we may not see acidogenesis step over there. Okay. And it could directly form the acetate. So, there are different group of bacteria also act upon. There are fermentative bacteria which are responsible for hydrolysis or acidogenesis, there are acetogens which are responsible for acetogenesis. So, they convert kind of this, and hydrogen can also be converted to acetate hydrogen and carbon dioxide. And then there are primarily two different groups of methanogens which leads to the methanogenesis, and these are the acetoclastic methanogens and hydrogenotrophic methanogens. So, hydrogenotrophic methanogens are the one which reduce hydrogen carbon dioxide into methane, and acetoclastic methanogens are the one which convert acetate into methane. So, that way the methane production is achieved from the complex biopolymers. Okay. So, the anaerobic process, simply because this entire thing is done in the absence of oxygen, and the rate of the different processes could be different. Okay. So, whichsoever among all these steps or all these processes, whichever turn to be the lowest or the slowest process would eventually become rate limiting step. Okay. So, that is how the different steps in combination convert the soluble COD, or at times even the particulate COD, because through hydrolysis we can convert the insoluble or particulate form of the COD or particulate form of the organic matter into the soluble organic matter. That is what hydrolysis primarily aims for. So, whatsoever the COD present in the system can then be converted into the through the substantial steps to the final end product. So, these are the process. We will discuss the detail of all these steps, all these processes in the next class. Thank you.